All right, let's set the scene. You've been spending a better part of 6 weeks on an isolated DC to DC supply. It's a pretty modest design. It's 5 volts in, 5 volts out, a few hundred milliwatts, galvanic isolation for a field instrument. And you've been through the transformer selection, you've tuned the snubber, the output looks clean on the bench. And then you hand it off for pre-compliance testing, and the report comes back, but it's got a problem. And it's not an emissions problem, it's not even a regulation problem, but a creepage violation. The physical distance between your primary and secondary conductors on the PCB board is not meeting the requirement for your isolation class. So back to the layout it goes. And that's not a component failure, and it's not a calculation error. It's just something that didn't show up until a specific person looked at a very specific part of the design through a specific lens, and it happened at the worst possible time in the schedule. Now, that scenario is actually a lot more common than most engineers are going to want to admit. And it's just one of several ways that isolated power supply designs fail later on. And not in simulation, not in initial bench testing, but weeks or even months into the project when a fix is going to be expensive. So today we're going to talk about why that's going to happen and what the failure modes actually look like, but also what are your options for reducing that risk. Welcome to the What's Up podcast. You're listening to Worth Electronics What's Up radio podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronics specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical designs and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. Let's start off with why DC to DC is genuinely harder than non-isolated, because the difficulty isn't always obvious until you're really in it. And in a non-isolated buck converter, your ground is your ground. The reference is shared, the feedback path is straightforward, and while there are real design challenges around layout sensitivity and compensation, they're at least contained within a single electrical domain. At the moment you add galvanic isolation, you essentially split your board into two realms. So now you have a primary side and a secondary side that can't share a direct electrical connection. And suddenly, every part of your design that assumed a common reference needs to be reconsidered. Your feedback path has to cross the barrier. Your control loop has to function across two domains. Your transformer becomes a custom component, or at least a very carefully selected one with its own parasitics, its own core behavior, even its own contribution to your EMI profile. And then, on top of the electrical design, you have the physical isolation requirements. And creepage is the distance measured along the surface of a PCB. Clearance is the shortest distance through air. And both of these have minimum values set by safety standards. And those values depend on your working voltage, your pollution degree, and your isolation class. These are not guidelines. They are pass or fail criteria in safety testing. So the standard that most engineers are working under for industrial and IT equipment today, it is IEC 62368-1. The isolation type it defines, functional, basic, reinforced, and double, are not interchangeable. Functional isolation, for example, this provides no protection against electrical shock. It prevents ground loops and keeps different electrical domains from interfering with each other, which is what most low-voltage industrial bus isolation applications actually need. But if your end product has any path to a user or even a hazardous voltages, then you need to be specific about which isolation class applies. And that choice has different implications on your clearance and creepage numbers and your certification path. The practical tip here is simple, but it's often skipped. Work out your required isolation class and calculate your minimum creepage and clearance distances before you start the layout, not after. Those numbers are going to constrain your component placement and your copper routing in ways that are much easier to accommodate when the board is blank than when it's already built. Keep a copy of the relevant standard spacing tables open while you're laying out the isolation boundary. It takes an hour, and a layout respin costs a lot more. Now let's talk about optocouplers, because this is the failure mode that probably catches the most experienced engineers off guard. In a typical discrete isolated flyback design, the output voltage regulation feedback gets across the isolation barrier via the optocoupler. The primary side controller reads the optocoupler's output current to infer what's happening on the secondary side, and it adjusts duty cycle accordingly. That architecture works at room temperature with a fresh component in a controlled environment. But the problem is that optocoupler current transfer ratio, or CTR, is not stable. It degrades with temperature, it degrades over time, and a device that has a CTR of 100% at 25 degrees Celsius might drop to 50% or even lower at 85 degrees Celsius. After thousands of hours of operation at elevated temperature, that degradation does not recover. Your compensation network was designed around a specific CTR range, and if the CTR range drifts outside that range, your loop can go unstable. Now, in practice, this means that a design that passes every bench test and every initial qualification test can develop regulation problems in the field in units that have been running hot in an industrial enclosure for a year or two. It's a reliability issue that doesn't show up early, and engineers who get burned by it usually only learn about it the hard way. Now, there are a few ways to handle this in a discrete design. The most common way is to compensate across the full CTR range, minimum to maximum, across temperature and lifetime. That means that your compensation has to be conservative enough to stay stable under worst case conditions, which usually means sacrificing some loop bandwidth and transient response. So it's a real trade-off. Some designers avoid the optocoupler entirely by using primary side regulation, where the controller infers output voltage from the transformer's flyback wavelength or waveform rather than measuring it directly. And that removes the CTR dependency altogether. The trade-off is accuracy and transient performance, since primary side regulation is inherently less precise than direct output measurement. It's a good fit for those applications that really don't need tight regulation, but it's a poor fit for those that do. And a third option that's worth knowing about is digital isolators for the feedback path. These can replace the optocoupler in certain topologies with more predictable behavior over temperature and lifetime. Now, they're not a drop-in replacement, and they do add their own complexity, but for these high reliability designs where optocoupler aging is a big concern, then they are worth evaluating. Here's the thing about isolated power design. The problem isn't that impossible. Engineers solve it every day. The problem is how much of your design time, your layout iterations, and your test cycles it consumes, and how late in the project the unpredictable failures tend to surface. A typical discrete, isolated supply requires a transformer, either custom wound or carefully selected off-the-shelf part with the right turns ratio, leakage inductance, and interwinding capacitance. You need a snubber network to clamp the leakage inductance spike on the primary switch. You need your feedback path, optocoupler or otherwise, designed for stability across temperature as well as lifetime. And you need a layout that satisfies creepage and clearance, routes the highest DI and DT switching loops tightly, and keeps the feedback path away from noise sources. And you need it to verify EMC, regulation, and isolation in testing. There are a few things that these experienced designers are doing to reduce late-stage surprises. First, simulate the snubber early. Many of our engineers size the snubber on the bench by probing the switch node and tweaking it until the ringing looks acceptable. Now that works, but doing a basic simulation first gives you a starting point and then helps you understand the sensitivity before you're starting at a hot MOSFET. Next, build in a transformer evaluation phase. So if you're using an off-the-shelf transformer, order samples of 2 or 3 different candidates and then characterize them before you finalize your schematic around just one of them. Leakage inductance in particular varies more between parts than datasheets sometimes suggest. And then finally, do a creepage and clearance check as a formal design review step before the layout goes into fabrication. It sounds fairly obvious, but it is the exact kind of thing that gets skipped under scheduled pressure. And it's exactly the check that catches the failure from the opening story. Now, none of that eliminates the complexity. It just moves the failures earlier where they're cheaper to fix. With all of that as context, this is where integrated isolated DC to DC modules need a serious look. Not as a shortcut for engineers who can't do the design, but as a legitimate architectural choice when the power supply is not where you want to spend your engineering effort. An integrated isolated module has the transformer, switching elements, control circuitry, and typically the input and the output capacitors are all in a single package. The EMC behavior is generally better characterized. The isolation is pre-certified, so this means that the creepage and the clearance requirements already have been designed in and tested, and the isolation class is documented in the datasheet. Now, you're still going to need to maintain clearance at a system level around the module, but the barrier itself is not your unknown. The feedback architecture in these modules avoids the optocoupler CTR problem entirely. Most use self-oscillating topologies or primary side regulation, so there's no aging feedback component drifting your loop over time. You are still responsible for input filter design because the module does not include it and the EMC compliance depends on it. You're also responsible for thermal management because derating curves are real and an undersized thermal path at 85 degrees Celsius ambient is a field failure waiting to happen. And you're also responsible for the output voltage selection since most isolated modules in this power class offer fixed output voltages. Worth Elektronik's Magic isolated modules are one family worth knowing about in this space. The 3 isolated series are available in both through-hole and surface mount packages. They cover input voltages from 2.79 volts all the way up to 42 volts, and they are IEC 62368 compliant. If you want to evaluate a specific combination of input voltage, output voltage, and load current, then you can use Worth Elektronik's Red Expert tool. It actually has a power module designer that runs efficient calculations for you, and it's useful for some sanity checking margins before you commit to a layout. Best part is it's completely free. Now, these non-isolated modules are also worth mentioning. If your design doesn't require galvanic isolation and you're fighting discrete buck complexity, then the same integration benefits apply on the non-isolated side. But that is a topic for another episode. In the interest of being honest about the trade-offs, though, isolated modules aren't always the right answer for every situation. If you're producing in high volume and BOM cost is under a microscope, then a well-characterized discrete design will often win on unit economics. If your application needs a custom output voltage, multiple outputs, or tight regulation specs that a fixed output module doesn't meet, then you'll need a discrete approach. If you're working at power levels above a few watts, the module options thin out pretty quickly. And if your team already has a discrete, isolated design that works reliably and it's also fully characterized, then there's no need to replace it. The decision isn't about capability. It's about where you want to spend those engineering time and effort and where you're willing to accept risk. Here's the thought to leave with. A late-stage failure in an isolated power supply, it's not just going to cost you a respin. It costs you the schedule confidence that you had before that result came in. Everything downstream of that supply shifts. And in a product development cycle where hardware substitutions are expensive and time is the real constraint, that is a significant hit. The question worth asking early, before the schematic is finished, isn't, can we design this discrete? Because you probably can. The question is this the part of the design we want to focus on? If the answer is yes, design it properly and give it the time that it deserves. If the answer is no, there are options to know about. The complexity doesn't disappear either way, but you do get to decide where to spend your design time. If you're ready to get hands-on with your design, or if you want to get more information about the Magic Power modules, maybe order some samples, click on the available links in the description. You can also visit our website at www.we-online.com. And while we understand that most podcast streaming platforms have made the switch to video, some images or links may not be available yet. If you're unable to view pictures or the videos, whether you're driving or just busy and want to catch up later, visit our podcast page at www.we-online.com/podcast or check out the Worth Electronic Group YouTube page for all visuals and resources from this episode. You're listening to Worth Electronics What's Up radio podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronics specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.